Now we'll be looking at finding the power of complex numbers. That means we're going to take our complex number such as z is equal to a plus bi and raise it to some exponent. So now we have z to the n is equal to a plus bi to the n power. Now if we have our complex number in our trigonometric form, it's much easier to find the power of our complex number. To do that, we use what's known as De Moivre's theorem. Now, De Moivre's theorem states that if z is equal to r times cosine theta plus I sine theta, which is just a trig form of our complex number, then z to the n is equal to r raised to the n power times cosine of n times theta plus I times sine of n times theta. And this is actually a little easier than taking a plus bi and raise it to, say, for example, to the 6th or 7th power. And we'll demonstrate this by using an example right now. Here we have an example of using De Moivre's theorem to raise a complex number to an exponent or to a power. Our complex number is 2 plus 2i, and we're going to raise this to the 6th power. Since it's not in its trigonometric form, we first need to do that. So we need to find r. We know r is a squared plus b squared, and the square root of that, so that's 2 squared, which is 4, plus 4, which gives us 8, and the square root of 8, if we simplify this, 2 radical 2. So here we have our r. Next we need to find theta. Since it's our a and it's our b, we know theta is equal to, or tan theta is equal to b over a. So b over a would be equal to 1. Where tan theta is equal to 1 is where theta is equal to pi over 4. So we know theta is equal to pi over 4. So now we can substitute this in our trigonometric form. So here we have 2 radical 2, which is our r, times cosine of theta, which is pi over 4, plus I sine of pi over 4, all now being raised to the 6th power. According to De Moivre's theorem, we can now take our r and raise it to the 6th power and multiply theta by 6. Now it's just a matter of simplifying this. So 2 radical 2 to the 6th power will give us 512. Cosine of 6 pi times 4 reduces to 3 pi over 2. So now we have cosine of 3 pi over 2 plus I sine of 3 pi over 2. We know from our unit circle that the cosine of 3 pi over 2 is 0, and that the sine of 3 pi over 2 is negative 1. So if we distribute this, we get 512 times 0, so that goes away, times 512 times negative 1 times I. So our final answer in standard form would be negative 512i, since there is no real part to this number. Now let's look at finding the reverse of raising a complex number to a power. And that is to find the root of a complex number. To find the root of a complex number, we first want to write that complex number in its trigonometric form, which is z is equal to r times cosine of theta plus I times the sine of theta. To find the nth root of this complex number, we find the nth root of r times cosine of theta plus 2 pi k over the root n plus I times the sine of theta plus 2 pi k over the root of that we're finding again. Now k is equal to 0, 1, 2, 3, up to 1 less than the root we're finding. So if we're finding the 4th root, then k would be equal to 0, 1, 2, 3, since it's 1 less than the 4th root, or 1 less than 4, which is 3. If we're finding the 7th root, then k is equal to 0, 1, 2, 3, 4, 5, and 6. Once again, 1 less than the root we're finding. So here we have to substitute 0 for k. So we're going to do all of this with k is equal to 0. After we've evaluated that, we have to redo the exact thing with k is equal to 1. And then we have to do it again when k is equal to 2. And again when k is equal to 3. So to find all 4 roots, we need to evaluate this when k is equal to 0, 1, 2, and 3. if we're finding the 7th root, we need to evaluate this when k is equal to 0, 1, 2, 3, 4, 5, 6, and so on. So to find the nth root, we need to establish what k is and substitute it in this formula n number of times. Now we'll look at an example of finding the root of a complex number. Here we're given that the complex number is 8 times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3, and we're required to find the cube root of that complex number. So to find the cube root of this complex number, if you remember from our formula, it's a cube root of r, so r is 8, so it's going to be the cube root of r times the cosine of theta, which is 2 pi over 3 plus 2 pi times k. Now since we're finding the cube root, our k will be equal to 0, 1, or 2. So we need to substitute for k 3 times. So we're going to substitute k is equal to 0, k is equal to 1, and k is equal to 2. We're going to substitute for k here and here. So now we have the cube root of 8 times the cosine of 2 pi over 3 plus 2 pi times 0 all over 3 plus I times the sine of 2 pi over 3 plus 2 pi times 0 over 3. Now all this expression here simplifies to 2 pi over 9. So this becomes the cube root of 8, which is 2. So this is 2 times the cosine of 2 pi over 9 plus I sine of 2 pi over 9. Now when we find this sine of 2 pi, cosine of 2 pi over 9 and multiply it by 2, this gives us 1.53. So all of this line here will simplify to give us 1.53 plus 1.29i. Similarly, when we simplify this, we get 8 pi over 9. So the cosine of 8 pi over 9 times 2 will give us negative 1.88. And the sine of 8 pi over 9 times I will give us 0.68i. So when we simplify this, we will get this piece. And when we simplify the third expression, when k is equal to 2, we get 0.35 minus 1.97i. These three pairs of numbers represent the solution or the cube root of our complex number. So here's the first root in standard form, the second root in standard form, and our third root in standard form. Now if we're to graph this, here we have our real axis and our imaginary axis. The graph of our complex number, our solution, this will be equal to the cube root of 8, which is 2. So our radius for our graph will always be the nth root of whatever r is. So here, because we're finding the cube root of 8, our radius is equal to 2. So our radius is equal to 2. And our theta would be first 2 pi over 9, which is what all is simplified to give. Our second angle would be 8 pi over 9, and our third angle would be 14 pi over 9. So here's the graph of our root, and here's the solution of our root. Now let's use our formula to find the nth root to solve an equation. Here we're given that our equation is x to the 4th plus 16i is equal to 0. Now if we subtract 16i from both sides, we have x to the 4th is equal to negative 16i. We can see that negative 16i is a complex number. Here the r would be equal to 16, because it would be a squared plus b squared, and the square root of that gives us back 16, since our a is equal to 0. Theta for this would be equal to 3 pi over 2, since it's negative 16i. So we have r and we have theta. So we can rewrite this complex number in the form of r times cosine theta plus I times sine theta. So now we have x to the 4th is equal to r cosine theta, or cosine of 3 pi over 2, plus I sine of 3 pi over 2. Now that we have done that, we can use the formula that we just used on the previous example to find all 4 roots of x. So the 4th root of x would be equal to the 4th root of r times the cosine of theta, which is 3 pi over 2, plus 2 pi k over n, and n here is equal to 4, So because we're finding the fourth root here, we're going to substitute k is equal to 0, 1, 2, and 3. So when k is equal to 0, this comes out to be 0.77 plus 1.85i. When k is equal to 1, then we have negative 1.85 plus 0.77i. When k is equal to 2, we have negative 0.77 minus 1.85i. And when k is equal to 3, we have 1.85 minus 0.77i. So here we have all four roots of x. So the solution for this equation would be these four complex numbers.